Hi there, my name is Larry Dunleavy. I'm a professor in the Department of Electrical Engineering, and today I want to talk a little bit about the WAMI Lab and how it started. But first, I've been here at the University of South Florida since 1990, teaching RF and microwave circuit design and measurements. In 1997, we founded what's called the WAMI Lab, and that was done with the help of National Science Foundation and a grant from Hewlett-Packard Company, which has kind of evolved into Keysight Technologies, which continues to be a strong supporter of the lab. Over the years, we've been able to partner with industry through what was originally the WAMI Advisory Board and is now called the WAMI External Affiliates Board, or the EAB. So through various donations from these companies, we've been able to keep this lab up to date, both getting feedback on the experiments and also getting some resources needed to kind of keep the equipment up to date. We're probably in our third or fourth generation of equipment now, which is really awesome for the students and what we can teach in this lab.
My name is Jing Wang. I'm an endowed professor in electrical engineering and also the co-director for the WAMI Center. I joined USF since 2006 after graduating from University of Michigan with 2 master's degrees, 1 PhD degree. For this semester, I'm teaching a wireless circuit and system lab, which is oftentimes referred as WAMI Lab, since it's physical instructional lab space. In a typical semester of WAMI Lab, you will learn how to test each of the building block components for a heterodyne receiver, and also you're able to design, test, analyze the performance of those components, such as a receiver we're putting together at the end of the semester that has a low noise amplifier, antenna at the front end, a mixer, a local oscillator, and then you're converting the signal back into a spectrum analyzer into the intermediate frequency, in this case at 70 megahertz, down from the 950 megahertz at the front end. One of the very important characteristics for a receiver, of course, is the conversion gain. You want to get the conversion gain to determine the sensitivity of your receiver, and by having a sensitive receiver, you can detect weak signal that may travel to you from a cell phone tower from a long distance away. Meanwhile, you cannot have this receiver having too much gain. Otherwise, your signal coming to the frequency of interest at high power may saturate your receiver. To summarize, WAMI Lab is a signature course for the WAMI Center. It has an international recognized reputation. Many universities are taking the same path to follow our course as a model. So you can enter USF by first taking the entry-level WAMI course, followed by a sequence of other RF and microwave courses to be successfully trained into RF and microwave engineer. In today's time, 5G, millimeter wave, Internet of Things, all demanding your knowledge on microwave engineering concept and hands-on skills.
Hello everyone, I am Gökhan Mumcu. I'm a professor in the Electrical Engineering Department of University of South Florida. I joined USF in 2009, pretty much right after getting my PhD from the Ohio State University. This year I'm teaching the EE Science 2 laboratory. It's a core course for our all electrical engineering students. The course is like an introduction to electromagnetics. They see electrostatics, magnetostatics, time-varying fields, and wave propagation. Different than the old-style electromagnetics course, this one actually that we teach here has a 1-credit lab component, and the lab is being carried out in the WAMI Lab. Experiments are introducing them to wave concepts. Some of them are through MATLAB, like this one over here shows the 3D propagation of a plane wave. Another experiment you see over here is the optics experiment, and it's actually designed to introduce them to the concept of wave polarization. So in this experiment, they can change the polarization of the wave that is being sent with the laser diode, and in the oscilloscope they can observe how much the power level is going down, and from there they can relate it to the fundamental properties of the polarization match or mismatch. And another experiment they do towards the end of the course is about this standing wave ratio measurement. So we have this coaxial cable with different probing locations, and they can put a VNA, excite it, and then probe at different locations to see the standing waves across this coaxial cable. So it's pretty hands-on course, and I'm thinking that our students are enjoying it, and many of them continue to the more advanced WAMI Lab.
My name is Stavros Vakalis, and I just joined the Department of Electrical Engineering and the WAMI group at University of South Florida as an assistant professor. I received my PhD from Michigan State University this August 2022. This spring semester, 2023, I will be offering the class Wireless Communication Systems Lab. In this class, students are getting hands-on experience with digital communications and wireless communication systems. So students learn to analyze, simulate, model, but also measure actual communication systems. It is a very unique class that is offered here at USF, where students don't just learn the theory, but they also test in real life the actual communication system. So these plots here are actually part of the lab bench, where students get to plot frequency domain, time domain power, a constellation diagram of a 16 QAM signal, and also an IA diagram. And additionally, in this course, students also get to explore the effect of radio impairments, what they can do when things don't go as expected, and they get an introduction to adjacent areas such as wireless sensing and software-defined radio.
In the first iteration of the lab, we had 6 benches that each had a spectrum analyzer, a vector network analyzer, oscilloscope, power supplies, a computer, and so on. And this was really the first generation network analyzer. It still works, but if we kind of fast forward to the modern lab now, we have, these are called PXI-based network analyzer, vector signal analyzer combinations, and these go to higher frequencies, 9 or 26.5 gigahertz respectively, and these allow us to perform the network and spectrum measurements. Another sort of legacy, this is kind of the middle, sort of probably about generation 2 spectrum analyzer is still available. This is a traditional spectrum analyzer. Some of the equipment on this bench goes beyond the original, and the course I want to talk about today is the RF and microwave measurement course. It goes deeper into various types of measurements that students may touch on briefly in what we call the WAMI class. The setup that I'm showing you right here is a 1 dB power compression measurement, and this is an example of a nonlinear measurement. And on the display we see an amplifier's gain where we're sweeping power. And as we sweep power on the network analyzer display, we see the gain eventually is compressing and dropping, and a common measurement in figure of merit used for components like amplifiers is the 1 dB compression, where the gain drops by 1 dB. We're also showing on the vector signal analyzer display, as the power is sweeping, we can see the fundamental power coming up, but also the harmonic second and third. So it's the nonlinearities that are causing this. And some of the supplemental equipment that's provided by one of our really long-standing sponsors and EAB members, Mini Circuits, is a programmable attenuator, USB-based power sensor, also a signal generator, which is used in this experiment. We're just not using it in this part right now. So in the RF and microwave measurement course, we perform, what I look at is the fundamental measurements are power, spectrum, noise, and network analyzer measurements. We take the students through about 10 or 11 experiments. And one of the things the students like a lot is learning how to do on-wafer probing, which is one of the very sort of popular ways that people these days make measurements on wafers, even on boards and so on. And what we're showing here is a miniature probe station. They all learn in 3 different experiments to get comfortable with probing. First of all, just generic calibration substrates, and eventually it leads up to probing a monolithic microwave integrated circuit device like the one shown on the screen here. And they learn how to bias up a transistor and measure gain and stability factor, which they can all calculate using the circuit simulation programs like Keysight ADS, which is used in almost all of our classes.